So we thought we start you off simple, very simple problem, very nice problem, and then Sabah will take the wheel. So, okay, let me share my screen. Um, can you see my screen?
Yeah, yes, we can.
Okay. So the problem, it's in the chat. It's zigzag conversions. Pretty simple, but it took me embarrassingly long to actually understand it. So that's gonna be fun. So basically, you get a string. The string PayPal is hiring, and then you convert it into a zigzag manner. So if you follow the zigzag here, it's PayPal is hiring, just in a zigzag manner. But that's that's it. And the output will be like they want to see what's, and that is not what I wanted. The output will be like no. On the first row, followed by the second, followed by the third, followed by the fourth. It would be the rows, but they all in a single string.
Anna, could you please read the description for us?
Yeah. The string PayPal is hiring is written in a zigzag pattern on a given number of rows like this. You may want to display this pattern in a fixed font for okay, and then read line by line. So basically row by row. They tell you how many row you're gonna have. So in the example I'm gonna solve, I it's 4 rows, but it could be 3, it could be 2, it could be one. Construction for rows is from 1 to 1,000. They will give you the number of rows, and for the string it could be also from 1 to 1,000. Is the problem clear enough? Uh,
Clear.
I will take the answer as yes, which is, of course, it is yes. Then, okay. So basically, how do we get that? What the first thing that came to my mind was God. So we will just loop through the string. Character by character, we loop through the string. But what right now I have no idea how to get out of it. So that's gonna be fun. Let me just uh, stop it for now. Okay, that's it done. Okay. My first idea was to use a hash, so I can keep like every row and the content in every row. Because my first idea is always to use a hash. But then there is a simpler one actually. Anyway, so let's just like whatever the result structure will be, we get the result, and we get the number of rows to keep track of which row we are in, and then we will use some sort of flag to figure out if we are going. Okay, so the problem that actually like made this problem took me so long is how do I know. So the first thing, I will look through the string, and let's just say I will take, let's make it the result as a hash first, and then I have the row. Let's say the row will start at 0. So what took so long about it was, so in the loop I will first I will say, let's not that result row, and then I will add to it the the extra the character of the string. But then I will reach the end row, and then how will I know if I am going? Then I will need to go like to lose a step, so not incriminate but decriminate. So that was actually like, the solution is actually quite simple. I'll just use the flag, which will make it 1. So when I am, if I am going, if I am at the 0 row, the flag is 1. So in the loop, I will just increase by 1, increase the flag by increase the row by the flag. So if I am going from 0, then the flag is 1, then the row will increment by 1. But if I am at the last row, the flag changes into -1. That means the row will, as I increase by the flag, it will decriminate. So I can just go down a step. I think it will be better in code. So let's just uh, so what's better than the hash is using just a simple array, but we know it's gonna have the number of rows in and then we have like the rows, which will start at 0, and we will have the flag, which gonna be 1, and then we'll start the 4 character in string s, not floor 4. That's lovely. So result row plus equal c. If I am at the if the row equal 0, then the flag will equal 1. But if the row is equal num rows -1, then the flag will equal -1, and in every loop, the row will increase by the flag, not by 1, by the flag. Let's just print that and see what do we get result, and just let's run it. So doesn't matter because I didn't actually return anything yet. I just want to print and see the result. So let's see. For the for a number of row 3, here here is the first row, which is, yeah, that's the actual expected result. Here's second row, which is yes, and here is the third row. So let's try to return it. Return result. And it will be accepted. But if I actually submit that, it will not pass. So there is one edge case left. So what if the number of rows only one? So if the number of rows is only one, I don't need to do any of this because I will only return the string. So we just need to take care of it. If num rows equal one, return string and submit. It passes pretty fast. Yeah, that's it. That's just a warm up. Sabah is going next,
Good job, Manna. That was
and I will not touch. There is another way to do it, but I will not touch it because it's involved a lot of mathing that's not gonna mess. So I am not gonna touch it. Anyone has any question about the other way? You have Sabah for it. uh, I'm good for now. So Sabah, take the wheels.
great. If anybody else has any like way of solving that, they can drop that in the chat or in the yes, in the chat. Okay. All right. So the second lead code we're doing today is minimum height tree. So we have a tree. So a tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without a simple cycle or simple cycles is a tree. So basically, we cannot have loops, is what they say, cycles. So this is a tree made out of graphs. Graphs basically a 2D array with two elements, right? And if you have enough of those, you can make a tree. And it's called a tree only if it doesn't form a loop. So given a tree of n nodes labeled from 0 to n minus 1 in an array of n minus 1 edges, where we have, again, two elements in the array, indicates that there is an undirected edge between the two nodes, A and B, in the tree. You can choose any nodes in the tree as a root, where you select the node X as a root. The result tree has a height H. So basically, you have a tree, right? And any element of that tree can technically be a root of that tree. And if you select that element as a root, then the height of the tree is basically h. Among all the possible rooted trees, those with the minimum height are called minimum height trees. So, for example, you can have as many variation or as many like choices of root, right? As many as the elements in your tree, but the only minimum height trees are made from roots that give us the minimum height. I'm not sure if I'm explaining that clearly enough, but a minimum height tree is the, I guess, the variation of a tree with the minimum height possible. So for example, this example we have 4n. That means we have four elements. And we have edges 0 to 1, 1 to 2, and 1 to 3, right? We have three like different combinations or different variations of ways, right? For example, the first tree is with a root of 0. The second tree has a root of 1, 2, and 3, right? And you can see the difference. Let's take this here. Okay. So in this case, we have 1, 2, right? We have two, I guess, edges. In this case, then the height equals 2. In this case, we only have 1, so the height is 1. In this case, we have 2 and then 2, right? So the minimum height tree in this situation would be 1, because this has a height of 1. This has a height of 2, 2, and 2, right? So the result of, like, what would our code return in this case should be 1, because we are returning the list of all minimum height tree roots, right? So we're returning the roots that would give us a tree, or that would make up a tree with the minimum height. So we're returning all the minimum height trees root labels. You can return the answer in any order. The height of a root tree is the number of edges on the longest downward path between the root and the leaf. So this is the root, these are the leaves, and the so it says the number of edges on the longest downward path. In this case, one edge to edge. The height of this tree is 2. Is it clear? Yes or no?
Yes.
Good. All right. For example, in this second variation, right, we have two, 1, 2, 3, 4, 5, 6. We have 6 elements, so n is gonna be 6, right? We have our edges, right? So basically it just gives us how these elements are interconnected. So we have 0 to 3, 1 to 3, 2 to 3, 3, 4 to 3, and then 5 to 4, right? And another variation of this that would give us the same height is this variation, right? So in this case, 3 is the root and is connected to all 4 elements, and the fourth one is connected to 5. And if 4 is the root, then it's basically the same height. The height is 2. We could, for example, start with 0, and then 0 would go to 1 to 3, and then 3 to 4, and then 4 to 5, and that would give us 3 as height. We could start as the same way from 1, from 2, from 5, and we would get a height that is bigger than this minimum. I hope that was clear enough. So n cannot be smaller than 1. The lengths are necessarily, the length is necessarily like as many elements as they give us in n. And yeah, we cannot have values bigger than n. So it necessarily starts from 0, 1, 2, 3, 4 until n minus 1. And we don't have repeat elements. The elements are distinct, and it is guaranteed to be a tree and no repeat edges. And it is a tree, so there won't be any loops or anything. Is that clear? And if yes, does anybody have any idea on how we can solve this?
Uh, would we perhaps look for the edge with the most connections, and then maybe make that one the root node first, and then attempt to find the one with the second most edges, I think, and then something like that, maybe?
All right, yeah, yeah. I forgot to, I guess, make an observation here. So in this case, you can see that in the first example, we had like one output and like one element in our list. And in the second, we had 2. Technically, we have like 3 cases. Either we would have no elements, and And in that case, I believe we should be returning a 0. In that case, for example, if we have an n of 1, right? We have only like one element. In that case, I guess technically we only have two cases. So the case where we're returning one element, and the case where we're returning two elements. So if we're returning one element, then there is one tree with the minimum height, right? So for example, we have like an odd an odd number of n. So for example, like this, right? And we have this root. This tree is probably going to be, or this root is going to be the minimum height, because it cannot be like a three, like a two edges, right? So this variation is going to be the minimum, right? So in this case, we're returning one element. If we have, for example, something like this, where we have two two possible nodes that would give us the minimum height tree. So in this case, for example, 3 and 4, right? Both of them would give us the minimum height tree. So both of them can be returned, right? So that is, these are the only two possible ways. Either we have one element in return, or we have two elements in the return, and that's it. We cannot have three elements, because then we one of them would have like a lower height. I hope that made sense. But if we had two elements our tree, not all three of them can be possibly like minimum height trees, or they could make minimum height trees in like as roots. I hope that was clear. Okay, back to Nyangasi's idea. We said that we could let's take this as an example. So if we take this as an example, you said that we look for elements that are connected the most, and then you keep going. Is that what you said?
Yes. We take the one with the most common, I mean, with the most, how to say, edges. And then, you know what I mean? Then we build the rest of the tree, and then we record its height. And then we try that with the one with the second most edges to see if it corresponds with the same height given the same way we built the tree. And then perhaps after that, we can maybe try a third one, but I doubt that would. I mean, yeah, we try a third one and see if that equally has the minimum size. And if it doesn't, I think maybe we can then assume that anything after that would be incorrect. But I don't know if that assumption is correct.
Okay, so you said basically we're building the tree from the
I believe,
most, I guess, common element, right? Or more
yeah, the one
scalable
with,
element.
yes, 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 the most common, or the one with the most edges.
And then you calculate the height for each of those,
Yeah,
right?
yeah, for the initial one with the most common edge. I mean, the most edge, the one that shows up the most.
Okay. I've explored that idea on my own. It was not efficient enough for our dearest LeetCode. I believe I did that. Yeah.
My middle name is inefficient.
But yeah, it did not. Basically, I not only looked for the I don't think I started with the most common elements, but I did try to find the height for the elements up to the minimum. And if it is minimum, you return -1 and you don't explore it. But even that, it was not efficient enough of like to try to build the tree and calculate its height. So there is another avenue we could explore, is instead of going from the top down, we could go from down and up. We almost like remove leaves as you go, right? And when you have either one element or two elements left, then those are your answers. So, for example, in this case, right, you can you can remove the leaves, the ones that have only one connections, right? So you have 3, you have 2, and you have 1, right? And once you go through, I guess, our first iteration of that, whatever left, either 1 or 2 or more, then you would make a decision based on that. If it is only 1, then that is your root, your most like your minimum height root. If it is 2, then those are the two, like in this case, right? You go 0, 1, 2, and then 5, and you have 2 left who that are like basically leaves in this case, but are our roots. And once you go to the second iteration, we decide if you have 1, as I said, you return it. If you have 2, you return it. If you have more than 2, aka you still are connected somehow, then you repeat that. You remove those leaves until basically you're left with 1 or 2. And it goes back to what I explained earlier of if you have 1, if you have 2, and then if you have more. And the only possible returns of like minimum height trees are either 1 root or 2, and you cannot go more. Was that clear? If yes, then we can maybe start making some pseudocode. If no, I can repeat that. I can re-explain it. Yes or no? Okay. Alright, so let's start with making some pseudocode. First of all, we want to know the connection that each node has. So we're almost gonna make a hash map, but made out of connections, not like the number of, I guess, appearances. So if we were to make a little hash map of our connections. For example, in this case, the value would be, or the keys would be the nodes themselves, and the values would be a list of their connections, a list of nodes that are connected to them. So in this case, if I make this 1, 2, 3, and that was not, that's okay. All right. So in this case, 1 is only connected to 3. So in here, it would be a list with 3 as the only node that is connected to 1. Moving on, 2, or I guess 0 is connected to 3. 1 is also connected to only 3. We have 2 with the same thing. Now for 4, or for 3, let's go to 3 first. Let's go here. And in this case, 3 is connected to 0, to 1, to 2, and to 4. So these are the connections of 3. 3 is connected to 0, to 1, to 2, and to 4. And if now we go to 4, 4 is connected to both 3 and 5. 3 and 5. And then 5 is only connected to 4. Now this way we have I guess, a visual way, or like a map almost, that would allow us to quantify the connections that each node has. 4 is connected to 5 is connected to only 4, right? So now from here we can know visually what kind of, or even in code, we have a way to know which nodes are leaves. So in this case, 0 is a leaf, it's only connected to 3. 1 is a leaf, it's only connected to 3. 2 is a leaf, only connected to 3. 3 is not a leaf, right? 4 is not a leaf, but 5 is a leaf. So in this case, we can remove all of these, right? And remove them from here. So I would remove 5 because I removed it from here. I would remove 0, I would remove 1, and I'd remove 2. And technically now, 3 and 4 are also leaves. If there are more elements, then we maybe could like repeat that loop of going through. But in this case, we only have 2 elements left. So in this case, we would only return these 2 elements. So in our code, what we're gonna need to do is map out the connections, right? And then the second step is to, I guess, calculate, or I guess just note down the leaves, save, save the leaves in like maybe an array, right? And then iterate through our, all right, moving on. If now that we have our leaves, we iterate through them, right? So we loop through these or like leaves, and then what do? We remove them from our map, right? If they exist, then we remove them. Of course they exist. Then we remove them from every like element, right? So for example, 0 is removed here, and 1 is removed, and then 2 is removed, but we like this connection, right, should also remove its connection to 0, right, as if it doesn't exist. So this 3, once 0 is removed from the map, or even if we don't remove it, we just remove it, for example, from the leaves, this 3 needs to also remove 0, right? So if it could, like, we check if it is also a leaf. So for example, let's try to make an example. Let's for example, this is 3, this is 0, 1, and then perhaps this is not our minimum height root. Perhaps there's also more to the side. But if we remove 0, right, then 1 should also be a tree, should also be a leaf. Then we remove 1. Then in this case, 3 is also a leaf, right? A leaf. And if there are more elements to this tree, then it also should be removed. For example, like this, and then like this, like this. If we remove these two, then this should also be removed, and these, until you find your root. So we keep iterating over the leaves until we have either one element or 2 elements. If we have more, then the loop keeps going. So that sounds to me like a while loop. So while leaves, or length of leaves, I guess, is bigger than 2, right? Because if it is 2, or if it is less than 2, then it should just return leaves. Then we loop through leaves, and then what do? We remove the leaf, obviously, but we also remove the connection from 3. So for example, if we I guess remove leaf. Okay, so you remove the leaf from leaves, right? And you remove the connection. You remove the connection of that leaf. So if I remove 0, then I remove this connection. So I remove 0 from 3. So I go to this tree and I remove its 0, right? So now that I removed the connection to that leaf, or I guess to, not of, to that leaf, I check if now this connection, if it is also a leaf. now that I've removed it. So for example, once I remove 5, right, I will remove 5 from 4. If I go here and I remove 5, now 4 is a leaf because its only connection is to 3. So we check. So we check if the connection or the neighbor, let's call it neighbor. So we check if the neighbor is a new leaf, right? So if it is, then we add it to the leaves, we add it to the array. I believe then we can be like, we can use some sort of queue, but I've only done it with an array. But I guess we could use a queue. That sounds like a possible way to do it. So we add the new leaf, right? Add it to leaves. And then you keep going until at the end your leaves only have 2 elements. So here in pseudocode we put it like this, but I guess we could make like new leaves equal, for example, like an empty array. So this we add it to new leaves, and then at the end we put like leaves equal new leaves. So just so the while loop can keep going. But I believe at the end, once leaves is smaller than or equal to 2, then we just return leaves. Does it make sense? Yes or no? Okay, sounds good. Now we can put that in here and try to codify it. So, map out the connections. How would we do that? We would just go through these elements, right? We would initiate a dictionary, for example, and we would go through these elements and just put it the same way we did here. So this would be the key, and this would be the value. And I guess the default value could be an empty array. There is a dictionary, I guess type, a data type called default dict. I don't think it's necessary to use that, but we could. That would default you to a certain type or data type based on what you obviously put, and you don't need to check if the element exists or not. But it is not necessary, as I said. So I see a question in the comments. What if the node has only one leaf? So that means that there are 2 nodes, and one of them is a leaf to another. So both of them technically are going to be leaves, and both of them would be returned. That would be the same as something like this, right? And both of them are leaves, and both of them technically the length is 2, and so they are going to be returned as normal because both of them would give us a height of 1. So if this is the root, then this is the height is 1. If this one is the root, then the height is 1. So that checks out. That made sense? Okay, back to here. So we initialize a dictionary. So I guess D is a dictionary. And we loop through our input. So and I would give them X and Y. I could give them anything. So for X and Y in edges. So it would be X equals 0, Y equals, or X equals 3, Y equals 0, then X3, Y1. You see how that goes. And then D, X. So we need to append Y to X, right? So in this case, we have 0, right? We need to append 3 to the array, that is the value value of 0. So D, okay, there's one way we could do it, right? If we have, for example, D is an array that is made out of 1, 2, 3, I can almost concatenate it with another array the same way we do it in strings, right? So if I have, so D plus, for example, 5, it would concatenate these two arrays would be merged. So we can use that same principle in here to do dx or d dot get x, so we can give it a default to default to, right? And plus equal, and it would give us, or I guess just dx equal d dot get. So if it doesn't exist inside our dictionary, it would default to an empty array, then plus y. And the same thing we would do in here for y, x. And if I am now to print d, and I believe I should be returning something. So now if I return d, then 1 has 0, 2, 3. 0 has a connection of 1, 2 is connection of 1, 3 has a connection of 1. So now that we have our map, right, then now we can save the leaves, right? So I will make a new variable called leaves. Basically, it would be iterating through our dictionary and only getting the elements that have one value. We only record the keys where the element is basically an array of one, of length 1. So if I do something like key and key value, or I guess for and d dot items, right? Only if the length of the value equals 1. And we print that and we see what it gives us. Now it only gives us the elements. Sorry, we only have the elements that have only one connection, basically our leaves. So in this example, the leaves are 0, 2, and 3, and the other example, the leaves are 0, 1, 2, and 5. 0, 1, 2, and 5, exactly. Now moving on, if we iterate through our leaves, so we check if our leaves, the number, or yeah, we check if the length of our leaves or the number of leaves is bigger than 2. We initiate a new array to store the new, I guess, iteration of leaves, the new leaves that are going to be formed once we potentially remove the old leaves, right? So we loop through we loop through the leaves. So basically for leaf and leaves, right? So you remove the leaf from leaves. We technically don't need to do that, but since we are overriding the old leaves, since we're already iterating through that, I believe we don't need this, but we're removing the connection to that leaf, right? So let's do this. We need to first find what the neighbor is. Let's print d to keep it close by so we can look at it when we need to. Um, okay, all right. So now that we have that, so we first need to find what neighbor is it connected to, right? So we need to store that. So neighbor equals d of leaf, right? So d of 0 would give us the neighbor. And since this is an array and we know for sure this is like one element in this array, we can just do this to get the first element as an int rather than a list or an array. And then we remove the connection to that leaf. So we remove 0 from the neighbor. So we traverse to the neighbor, and that would give us this array. And if we use remove, that would remove one element of this array. So if we do remove leaf, which is 0, then it would remove 0 from this array. So does dot remove. I remove leaf. Let me make sure that this actually removes it from, for example, d, and then d dot remove, for example, 2. Then yeah, it is changed. Then we don't have to assign it to the, okay, that's good. And then now that we remove the connection of that leaf, we check if this d neighbor, if it is a leaf. And how we do that? The same way here. We check if the length of it is equal 1. So I'll take that. And if d neighbor, or the length of d neighbor, equals 1. If it is, then we add it to new leaves. So new leaves dot append our, yeah, neighbor. Now in this new version of leaves, we have the second, I guess, version. We have the new leaves that are formed. I will not answer that, Mangas. So the new leaves basically are going to be assigned to leaves. So now when the new iteration comes, we check this variable if the number of leaves in it is bigger than 2. If yes, we keep going through the loop. If not, then we just return leaves. I will remove this print and let's run that. Okay, that passed. And let's submit. And I don't think this will submit because there is one test case that, yeah, one edge case where n equals 1. So we just add that here. So if n equals 1, then we just return an empty array with, not empty array, but I guess an array with, let's add that here, an array with 0. Even though I don't technically understand why 0 should be an empty, but no, not an issue. If we submit it, oh, okay, let's see why. I might have missed something. So it is expected to give me 2, but it outputted 1 and 2. Let's add that and see. So it added that to the,
You said something about greater or equal to 2
yeah,
earlier,
yeah,
but on line 13 you only have a greater than. Could that be it?
yeah, but it should be inside the loop if it is greater than 2. So if it is
Okay,
less than 2 or equal to 2, it should leave the loop.
understood.
Okay. We can add print statements somewhere and make sure that we're recording the right elements. We can add that here and use maybe that here. So it didn't access the
Spooky.
so somehow leaves only have two elements. Oh, oh, then maybe this should be different. Maybe it is not the length of leaves. Because in any case, you should enter this loop. Okay, that makes sense. So for example, maybe we could record maybe the length of n. So almost like remainder n. So in this case, it would be n. And if n is bigger than 2 and we decrement n as we keep going, that should solve it, I think. Not sure. Oh, that did. That did. So basically, you just hold n and you keep removing elements. So you're not starting with leaves. You almost end with leaves, rather. I'm sure that made sense, but let's submit that. And yep, that, oh, that is a very bad score. Not sure what we did, but yep. Yeah. Another way to get, I guess, a better score than this, since apparently we took too little time and it's only 1 hour past. Let's try to take maybe another way to get less time. I remember Mena earlier said that using arrays is more efficient than using dictionaries. So we could, instead of this being, let's keep it as D, but it could be a list since, okay, let's, if we look at this dictionary, we know that it is ordered like 0, 1, 2, 3, 4, 5. And we know that we're not missing any elements, like based on the nature of the problem, right? We have as many elements as n minus 1, or as n, starting from 0, ending with n minus 1. We could take advantage of that information to make almost an array, and these numbers would be the indexes. Since it is 0, so the first element of that array would be index 0, 1, 2, 3, 4, 5, right? And you don't need to store the index 2. You only need to store the values, right? So we could have something like an empty, like an array of empty arrays, I guess. Yeah. And the number of that would be, I guess, n. Yeah, from 0 to n. Let's print that and see what it gives us. And let's return. No, that did not work. Alright, so it is. So we need an array of multiple arrays.
Don't you want to do one of those fancy list creation things with the for loop.
Well, I guess you could. You would do like, but this is supposed to be like a simpler way to do it. But you could for sure do for E in range, like for range n, and then d dot, you could initiate it with this, and d dot append like this. I mean, I guess this should work. Yeah, that's good. So this gives us 4 elements, as many elements as we have. Still, I know there is a shorter way to do this. Maybe
One
like
of those list composition things. I know what you're referring to. Yes, that thing.
range and do this. Okay, all right, that's better. Okay, so now that we have this, we can, I guess, tweak our code to handle a list of lists. So let's start with this. So for x, y in edges, now we know they exist, so we don't do this get. So we just do dx dot append y, and here dy dot append x. And if we print that, that is good. So it should give us, yeah. So the index 0, which is the element 0, is connected to 1. The so it's this case. The element 0 is connected to 1. The element 1 is connected to 0, 2, 3. The element 2 is connected to 1. Element 3 is connected to 1. Right? And then let's go here. So leaves its key for, and we don't have two elements. So for, I believe, for E, or for just, yeah, for E, in range or in D, let's just keep it in D, if the length of, this is value, right? So if, so it's val, or it's E. Nope, it is val. So in val, oh, yeah. So it's the index. We should also be recording the index. So the value is the actual array, right? But the index of it is what we need to record as a leaf. So the value for index value in, can do our enumerate trick, enumerate, yeah, if length of value equals 1. Let's see what this one will print. Nice. So it's, nope, that is not nice. So it's the index that we should be recording. Great. So our edges is 0, 2, and 3. So it records the edge for the, if the value, which is the array, equals 1. Basically, if our node only has one connection. Now, moving on, let's go here. Now, the remainder is the same, while leaves and -1. Now, d leaves, I believe this stays the same. D neighbor dot remove, this also stays the same. If length of d neighbor equals 1, then new leaves dot append. I don't believe there's anything to edit in this. Let's run it. Okay, that passed, and hopefully we get a better efficiency on this. Okay, definitely better. Definitely better from 7 to 49. Okay. But yeah, that's that is the solution for this problem. If anybody has a different, I guess, solution for it. Oh yes, yes,
Hello, good
background
evening.
noise. That does sound like something that would work. Okay.
Hello there.
Yes, yes. Hi.
Oh, yes, good evening.
Good
Uh,
evening.
I have a not really like an optimization, but a question actually. In the solution, we are actually cutting down like the number of leaves gradually until we find the last leaf that yeah until we find the last leaf. So won't like just uh like picking the longest um node with the largest number of connection work like uh in the beginning when you're using the hash table with the dictionary, then you had uh like I think like two, okay, it was 3 and 4. It had like 4 connections, or was that correct? Like 4 connections. So if you're like just picked that one instead of going through the other ones and like finding and shaving them off, like this is a leaf, skipping it, this is a leaf, skipping it. Why not just pick like a branch, like this has more than one connection, so we'll pick you, then we use that for yeah. So basically what I saw was all the non-branches were actually three and four. So uh, one connection. So is there like a have you looked at that? Is that
Could
a
you
possible
could
method?
you please repeat the last thing you said? It started breaking towards the end.
Oh, okay. I said and this diagram over here that as a result and pretty much the only two that had more than one connection. So 3 and 4 at the beginning, they gave the same result, or is there something different than that going on?
Again, it started breaking once you started to say what, like the main part. If you could just write that to make sure
Uh,
I fully understand it. But basically, you said we
okay,
start
okay
by
then.
taking into consideration only the nodes that have more than one connection. That I heard. And then what else?
Yes,
What do we do with that?
the node that has more than one, the node that had more than one connections, wouldn't that give us the result we're looking for? Or is there something deeper going on?
If we take this, for example,
Because the
how, okay, the possible outputs, as I said, either one or two. So in this case, right, let's go back here. We have two nodes that have more than one connection. But what if it's only one of them, or maybe both of them? How would we know? I want to maybe put down an example. Like for example, we have this. So these are, I guess, mm, okay, yeah, maybe we have like 3 or 4 elements that have more than one connection. How would we go about that? Hello?
Sorry, could you expand on that? Three
I
elements with
said,
more than one
what if we
connection.
have more than two elements that have more than one connection? How would we choose which ones actually? Because I don't believe the
Oh,
number of connections, because one node could have like a million that are just leaves, right? But which ones do we
oh,
choose? We
okay.
have, in this case, we have this one, and I believe you have this and this as like potential roots. But which ones do we choose? This one is the same
The
as
one in the
this.
middle.
But why?
Yeah,
How? Yeah.
that
How
is
would we
correct.
see that in code? I guess that's the question.
Uh,
Yeah.
okay, that makes sense.
Any. Thank you.
Thank you.
Any other questions? I will update it right now. Fine. Hope y'all are happy. Okay, if no more questions, then we can wrap up this session. It has been a quicker session than our previous one, but I guess that's the point. Thank you, Mena. Thank you, everyone who has made this session nice and interactive. And yeah, I hope to see you on, and Eid Mubarak, everyone who celebrates it. And yeah, see you next week.
Good night.